Hey guys, Professor Brown here, and this presentation is for OpenStax Chapter 4.4. And during this presentation, we will take a look at how Lewis structures are composed and how they help us predict the structure of covalent compounds. Before we dive into talking about Lewis structures, I want to do a quick callback to the idea of valence electrons, what they are, and how you figure out for an element how many it has. Valence electrons, if we remember from chapter 3, are defined as the electrons in the highest energy level for an atom. We have an example here on this slide, chlorine, and chlorine has 7 valence electrons. Chlorine has 7 valence electrons because its highest energy level is the 3rd energy level, and we can see that it has 7 electrons in that 3rd energy level. There are 2 in the 3s sublevel, and there are 5 in the 3p sublevel. Again, giving chlorine a total of 7 electrons. I wanted to take a look at bromine also with you to show you that it also has 7 valence electrons, which we would expect because it's found in the same column on the periodic table as chlorine does. But when you look at its electron configuration, some people may get a little confused and think maybe it has more valence electrons than the actual 7 that it has. And the reason for that is we may notice that in the electron configuration for bromine, we can kind of see that there is the 3D level in between the two 4s sublevels that we have, or the 4s and the 4p sublevel that we have. Now, that 3D sublevel is not considered the valence shell, even though it's a little bit higher in energy than the 4s sublevel. The 4th energy level is still the highest energy level in this atom or in bromine, and therefore the 4th energy level is the only one that's considered the valence shell, and so therefore bromine also has 7 valence electrons. So Lewis symbols are ways to depict pictorially how many valence electrons an atom or an ion has in a certain configuration. And all it does is uses dots around the element symbol to indicate the number of valence electrons in a species. We have 2 examples here on this slide. Calcium is in the 2nd column of the periodic table, and elements in the 2nd column of the periodic table have 2 valence electrons, and so the Lewis symbol for a neutral atom of calcium would be, as we can see here, the calcium symbol with 2 dots out to the side to indicate the 2 valence electrons. And then bromine, which we just looked at the electron configuration for and showed that it had 7 valence electrons. To draw the Lewis symbol for a neutral atom of bromine, we would write the capital B, lowercase r for the elemental symbol for bromine, and then put the 7 dots to indicate the 7 valence electrons around a neutral atom of bromine. So when you get asked to construct the Lewis symbol for an atom of an element, you can remember back to the periodic trend that we have identified for determining how many valence electrons are found in a specific element. And we can do that by looking at which column in the periodic table an element is found in. Those in the first column there, the alkali metals, all have 1 valence electron, and that's things in that row here. Things in the 2nd column here, you can see all the way down, have 2 valence electrons. In the transition metals in the middle here, there's not a trend to tell us how many valence electrons are found in those atoms, so we can't make predictions quite as easily with the transition metals, and we kind of shy away from those until we get a little bit more advanced. But then we move over to the P block of our main group elements, and we can see that the trend continues with 3, 4, 5, 6, 7, and 8 valence electrons respectively in each of those columns of the main groups of the periodic table. And so from that trend, we can then see that we would have a trend of repeating Lewis symbols for neutral atoms of these elements, with everything in the first column here only needing 1 dot to indicate 1 valence electron, everything in the second column only needing 2 dots to indicate 2 valence electrons, and so on and so forth in the right half of the main group, all the way up to our noble gases, where we would show 8 dots because they have 8 valence electrons. I want to take a moment and think about that idea that the noble gases all have 8 valence electrons. We learned earlier that atoms bond in order to obtain a configuration that resembles that of those noble gases, especially the ones they're closest to. So this is usually then a configuration that contains 8 valence electrons, which 2 of them are found in the S sublevel of that valence shell, and then 6 of them are found in the P sublevel of that valence shell, for a total of 8 valence electrons. And that leads to something we call the octet rule. As we are going through the following examples of atoms bonding together, it's important to keep in mind that atoms bond in order to achieve 8 valence electrons. And so most of these following structures won't be complete unless each atom has that 8 total valence electrons. This is what is known as the octet rule. On the next few slides, we will take a look at how Lewis structures can be used to give insight into the bonding of different compounds. We will start with the Lewis structures of ionic compounds because they're a little bit more simple than those for the covalent compounds. It's important to keep in mind that ionic compounds are composed of ions, so we know that electrons are being completely transferred from one atom to another. Usually, the atom that is losing the electrons is a metal atom of some sort, and the atom that is gaining the electrons or receiving the electrons from that metal atom is a non-metal atom of some sort. When we want to draw the dot diagrams, the Lewis symbols, if you will, of ions, there's a couple of different ways it's done. For cations, no electrons are going to be drawn to show that cations lose their electrons in order to obtain their octet. Now, that may be the hardest part to kind of figure out, because even though we don't depict it, the positive ions, the cations, they do have 8 valence electrons. When they lose their 1 or 2 or 3 electrons, then the energy level underneath their valence shell becomes the new valence shell. However, just as convention to show that they are losing electrons, we don't put 8 dots around the positive ion. We just imply that it's lost its electrons in its valence shell, and we indicate how many it loses by putting the typical charge in the superscript position. For anions, we do draw the 8 electrons. That indicates that they gained extra electrons from somewhere. They probably gained it from a metal ion. We also encase that ion in the square brackets that you see there to indicate that it is an ion. And then the charge is indicated for it as well in the superscript position outside of the brackets. On this slide here, we show how to put these ion symbols together in order to indicate how a compound is formed between the 2 ions. To show a complete Lewis structure for an ionic compound, what we do is we show the Lewis symbol of each ion in the compound. We make sure the charges are indicated for each ion and that they are correct. We make sure that the anion is encased in brackets as we indicated on the previous slide. And then finally, we indicate the appropriate amount of each ion in the subscript position. And that amount would be the same, that would be the same amount from the formula of the compound. In the first example that we see there, we can see that we have sodium chloride, and we've indicated that sodium chloride is composed of an Na plus ion and a Cl minus ion, which we've encased in brackets. We've indicated that each ion, respectively, the sodium ion has a positive 1 charge, even though the 1's not written, and the chlorine ion has 1 negative charge, even though the 1 isn't written, and we've simply placed them beside each other. There are no subscripts on these ions because there is only one of each ion in the sodium chloride molecule. We've done the same thing for magnesium oxide below it. Magnesium forms 2 plus ions, which we've indicated by writing Mg2+. Beside it, we've indicated that oxygen forms 2 minus ions. We've written an oxygen ion Lewis symbol with brackets, 8 electrons, and the 2 minus charge. Since you would only need one of each ion to balance the charges between the two of them, neither has a subscript, indicating that the formula for magnesium oxide is MgO. Finally, we have an example where we have more than one ion as part of our formula. In this case, this shows the bond between calcium and fluorine. Because calcium has a 2 plus charge from losing 2 electrons, and fluorine only has a 1 minus charge from gaining 1 electron, because it only has room to gain 1 electron. Therefore, we show that we have 2 fluorine ions in our formula. Well, that's where I'll stop. On this slide, we're going to draw some of the Lewis structures for the following given ions. And we can see that the first ion we're asked to give a Lewis symbol for is the astatine 3 minus ion. So astatine is found in the 15th column of the periodic table, and all of those elements have 5 valence electrons, and they gain 3 electrons in order to achieve the octet. And we know from the previous slides that when we draw an anion's Lewis symbol, then we are going to show the element symbol in a pair of square brackets, and we're going to indicate that the 3 electrons have already been gained from somewhere when the bonding occurred, and we indicate the charge on the ion in the upper right superscript position, and therefore the Lewis symbol for the astatine 3 minus ion looks like what you see on the screen there. In much similar fashion, iodine, he gains 1 electron in order to form his ion. And so when we draw iodine's anion Lewis symbol, then we show the symbol for iodine I in a set of square brackets. We go ahead and draw all 8 of the electrons around the iodine to indicate that that ion has gained the 1 electron in order to achieve the octet, in order to have the same configuration as its noble gas neighbor. And we still indicate the charge in the right superscript position. If it's just 1, as in the case here, 1 negative charge, it's not necessary to write the 1. You can just display the charge. For our next atom there, or our next ion there, we are asked to write the Lewis symbol for the beryllium 2+ ion. Beryllium is one of the alkaline earth metals in the second column of the periodic table, and because it is in the second column, we know that it forms 2+ ions. In other words, it likes to lose 2 electrons in order to achieve the noble gas configuration of its closest noble gas neighbor. And when we lose electrons, the convention is to not draw any electrons around the atom or ion symbol in order to show that those electrons have been lost. We still indicate the charge in the right superscript position, so essentially the Lewis symbol is just the same as what we see there on the slide. The Lewis symbol for the cation is just Be with the 2+ charge indicated. We don't put it in brackets, and we don't show any electrons because we want to imply that those electrons have been lost in order to form the ion. And then finally, we have the oxygen 2- ion. And as with our other anions, we will show oxygen and we will put 8 electrons around the oxygen because it gains 2 electrons to complete its octet. And by gaining 2 electrons to complete that octet, it gains a 2 negative overall charge. And so the Lewis symbol for the oxygen anion is as you see there. Here on this slide, we're going to do some more examples of writing Lewis symbols of some different ions. This time we've taken it a step further and we're going to identify what the charge is on the ion ourselves without it being given. To do this, we will remember that we have identified columns on the periodic table, the elements of which tend to form certain charged ions when they ionically bond. And those trends that we will remember look something like this. The elements in column 1 here, what we call the alkali metals, these all tend to form +1 ions or 1 positive ions. The elements in column 2, group 2 here, all tend to form 2 positive ions. The elements in the 13th group here all tend to form 3 positive ions. The elements in group 14 here all tend to form 4- ions. And the elements in group 15 all tend to form 3- ions. The elements in group 16 all tend to form 2- ions. And the elements in group 17 all tend to form 1- ion. So if you can kind of commit that trend to memory, you will always be able to identify what ion a certain element forms. Now, of course, we can see we don't have any trends here for our transition metals. Those can form varying ions, and so therefore you have to be given, if you're going to be asked a question concerning a transition metal, you'll be somehow indicated as to what the charge is. But for everything else, everything in what we call the main groups, the first 2 columns and the last 6 columns, you can infer what ion they typically form given the column that they're found in. And so if we're going to show the Lewis symbol for the ion formed by the calcium atom, we will remember that, or we will see that calcium is in the second column and therefore forms 2+ ions. We'll remember that for our cations, for those ions that have lost electrons to form ions, we don't draw any electrons around the atom and we don't put any brackets. We simply just leave it as your typical ion notation that you see there. So that Ca2+ would be how we would write the Lewis symbol for a typical calcium ion. Now, in the same vein, potassium is a alkali metal in the first column, and it forms +1 ions. So again, we're not going to show it with any electrons in order to write a Lewis symbol for your positive ions. So K with a plus in the superscript position would be enough to indicate the Lewis symbol for a potassium ion. Bromine is in the 17th column of the periodic table. And so therefore it forms 1- ions when it bonds ionically, and it does that because it requires one electron to be gained in order to complete its octet. When it does so, it then has 8 valence electrons, which we show for the anion Lewis symbols. We then enclose that Lewis symbol in a bracket to indicate that it's an ion, and we include its charge in the superscript position outside of those brackets. For strontium, we see that strontium is in the 2nd column of the periodic table. It therefore forms 2+ ions, and the Lewis symbol for your cations look like your standard ionic notation. So strontium would be Sr2+. Fluorine, much like bromine, is in the 17th column of the periodic table. So when it forms an ion, it does so by gaining 1 electron. And therefore, if we want to depict the Lewis symbol for the anion formed by fluorine, we will show it with all 8 electrons because it went out and gained that extra electron. We will encase it in square brackets because that's notation. And then we will add its charge in the superscript position. On this slide, we're going to combine it all together and write some Lewis structures for the following compounds. The first one we have is magnesium sulfide. So when we want to draw a Lewis structure for an ionic compound, we simply want to put the Lewis symbols for the ions that form the compound beside each other and indicate with some subscripts how many of those ions are there. So for the first one, we're going to first start by drawing the Lewis symbol for the magnesium ion. Magnesium forms 2+ ions, and so therefore its Lewis symbol is Mg2+. Remember, for the cations, not much changes. Actually, nothing changes. And for your sulfide anion, we will put our S as the symbol for sulfur. We will show that all of its electrons have been gained, and we will encase it in square brackets. We also need to indicate the charge of the sulfide anion, and we can figure that out from its position on the periodic table. It forms 2- ions. We can see from the formula here there is only 1 magnesium atom and 1 sulfur atom or ion in our formulas, and so we do not need any subscripts here or here because we don't write ones when we do chemical formulas. For the second one, we see we have aluminum oxide, and so to do the ionic Lewis structure for aluminum oxide, we will start by writing the Lewis symbol for the aluminum ion. Aluminum, inferred from its position on the periodic table, forms 3+ ions. And oxygen, from its position on the periodic table, forms 2- ions. We can see from the formula that there are 2 aluminum atoms for every 3 oxygen ions. So we can put 2 and 3 down here to indicate the numbers of each. And so that is how the Lewis structure for aluminum oxide would appear. The last one we have is gallium chloride. And so to do the Lewis structure for gallium chloride, we start with the Lewis symbol for gallium. We know from its position on the periodic table that gallium forms 3+ ions. Then we will write the structure of the chloride ion. As always, we indicate that it has gained the electrons, and so therefore we draw all 8 valence electrons around our chlorine ion. We indicate what charge is on each of those ions, and we indicate how many of those charges we have. So that is how the Lewis structure for gallium chloride would appear. When it comes to Lewis structures, for the most part, the ionic ones are pretty simple. You just determine what the structures or symbols of the ions you have are and place them beside each other and indicate the number of each. For covalent compounds, it's a little more complicated. Lewis structures of covalent compounds give us insight into the actual structure of each individual molecule. It kind of gives us an idea of which atoms are connected to each, which is a little bit more information that you will get from just a chemical formula. It actually kind of gives you a 3D idea of how the molecule is assembled. To do this and to predict these structures, there are a few simple rules with which are applied to build Lewis structures of covalent compounds. We need to refresh a few concepts first, and we will start with that on the next few slides. Here on this slide, we're going to take a quick relook at what is actually going on behind the scenes in a covalent bond. We can see we have 2 chlorine atoms here, and we are going to investigate how they covalently bond in order to achieve their octets. So chlorine, as a neutral atom, has 7 valence electrons that you can see outlined here on the slides. They have 2 electrons in the 3s sublevel, and they have 5 electrons in the 3p sublevel. The third energy level is its valence shell, its level of highest energy, and we can see there it has 7 valence electrons. And as with all other atoms, when they bond, they are trying to achieve that octet. And so when atoms covalently bond, what they do is they get together and they say, hey, if we share that last unpaired electron we have back and forth between each other kind of very rapidly, then it's like we do kind of satisfy that octet rule. We do have a share of those 8 electrons, even if it is just for a brief instant, having close to a share of those 8 electrons now because of that pair sharing allows the octet to be satisfied and allows the atoms to bond together, and in this case would give us a Cl2 molecule. So when we draw the Lewis structures of covalent compounds, when we combine the Lewis symbols of atoms together to show a covalent bond being formed, we show that bond with a line connected between the 2 atoms. And on the atoms, we also draw how many lone pairs of electrons are surrounding the atoms. You can see this is a model of the previous slide's covalent bond that we just looked at, the Cl2 molecule. There are 6 electrons around each of the chlorine atoms that are not involved in the bonding between the 2 atoms. There is 2 electrons here that are shared between the 2 atoms. And so we indicate that with the line that you see in this structure here. This most closely represents what you will see as the Lewis structure for the chlorine molecule, the Cl2 molecule. We see that each atom has satisfied its octet because each has 6 electrons that it has to itself, and it also shares 2 electrons due to the nature of the single bond with the other atom. This gives us a total of 8. This chlorine also has 6 electrons that it does not share with the other, and a share of the pair in the middle forming the covalent bond, giving it a total of 8. Both of these atoms have therefore satisfied their octet, and that is why this is a stable configuration for chlorine to bond into. Here on this slide, I want to make one little note about the octet rule, something that we will run into quite often as we are looking at these covalent Lewis structures. And that is a reminder that atoms are stable with 8 electrons in the valence shell. So throughout these Lewis structures, where we are going to try to be drawing structures in which each atom has a share of all 8 electrons. And there is one exception, however, and that exception is the element hydrogen, which only needs 2 electrons to satisfy its octet rule or have a stable configuration. There are many cases where it will be necessary for atoms to share more than 2 electrons in order for octet rules to be satisfied in molecules. We can see one of the most common examples here on this slide, and that is the CO2 molecule, more commonly known as carbon dioxide. We can see that between the carbon and each of the oxygen atoms, we have 4 electrons being shared. On the previous slides, we saw only 2 electrons being shared, which is what we will refer to from now on as a single covalent bond. When 4 electrons are shared between atoms, we call that a double covalent bond, or just a double bond. We indicate that 4 electrons are being shared between atoms by drawing 2 lines between the atoms in the molecule. Those 2 lines represent the 4 electrons being shared between the carbon and the oxygen atom circled. These 2 lines would indicate the other 4 electrons being shared between the carbon atom and the other oxygen atom. It is even necessary in some cases for atoms to share all the way up to 6 electrons between them in order for octets to be satisfied. When 6 electrons are shared between atoms in a molecule, as shown here with carbon monoxide, which is formed between 1 carbon atom and just 1 oxygen atom, in order for the octet to be satisfied for each atom, a triple bond must be formed. On this slide, you can obviously find the rules for how to predict the way a Lewis structure should appear. I'm not going to go through each one of these rules independently and explain each one. I think that's best done by example, which we'll see plenty of throughout the rest of this presentation. So I do suggest maybe you either pull these up on your phone or perhaps even print them out to have with you as you go through and practice some of these Lewis structures yourself and as you work on the Lewis structure assignment that is due in the next couple of weeks. For the first example, we are going to draw the Lewis structure for a molecule of fluorine, chemical formula F2. When we determine Lewis structures, the first step is to figure out how many valence electrons do we have to work with. We do that by counting how many valence electrons each atom in the molecule contributes. Because fluorine is found in the 17th row of the periodic table, we know that neutral atoms of chlorine have 7 valence electrons. Because we have 2 fluorines that make up our molecule, that means we have 14 total valence electrons to work with. The second step of the Lewis structure process is to determine the central atom and then connect everything to that central atom via single bonds. In a diatomic molecule, there is no central atom, so we do not need to worry about what the central atom is. We will just show our 2 F atoms connected by a single bond. Keep in mind that single bond represents 2 electrons. So we've already used 2 of our 14 valence electrons we have to work with, meaning we have 12 electrons left that we can place around the atoms in our molecule. But the third step is placing those leftover electrons around the terminal atoms, or atoms that are not the central atom. Since there is no central atom in our diatomic molecules, we will just place our 12 electrons around each of the 2 F atoms. I can put 6 around this fluorine atom, as well as 6 around that fluorine atom, using up all 12 of my electrons. I also may recognize now at this point that this fluorine atom has a share of 8 electrons. It has 6 electrons that it does not use to bond, and it has a share of those 2 electrons in the paired bonding electrons. This fluorine also has a set of 8 electrons, 6 non-bonding electrons and 2 in the bonding pair of electrons. They both, in this way, have satisfied their octet rules. And so this is a very good structure, a correct-looking Lewis structure for the F2 molecule. We want to check a few things when we get done drawing a good Lewis structure. The first is, have we drawn the correct number of valence electrons? I see 2, 4, 6, 8, 10, 12, 14 valence electrons. Since we had 14 here, that seems great. And we also want to make sure each atom has a full octet. That fluorine has 8 electrons there, and that fluorine has 8 electrons there, meaning that both have satisfied the octet, and that can be considered the correct Lewis structure for the F2 fluorine molecule. Now let's draw the Lewis structure for the oxygen, or O2 molecule. Oxygen sits in the 16th column of the periodic table, so oxygen has 6 valence electrons. We have 2 oxygen atoms in our oxygen molecule, meaning we have a total of 12 valence electrons with which we can build our molecule. The second step is to pick a central atom and then connect your atoms to the central atom. Now, of course, this again is a diatomic molecule with just 2 atoms, so there's no central atom. We will simply start by combining our atoms with a single covalent bond. By using that single covalent bond, we have already used up 2 of our electrons, and therefore we have 10 more electrons we are allowed to place throughout our molecule. I'm going to place 6 electrons on this oxygen, leaving me with 4 left over to place on the other oxygen. So we may stop there and assume that this is the correct Lewis structure for the oxygen molecule, but let's go and check and make sure all of the conditions are met. So we can see that this oxygen here has 2, 4, 6, 8 electrons. He has satisfied his octet. This oxygen here, however, only has 2, 4, 6 electrons. He has not satisfied the octet. So something has to be done. I'm going to redraw our current Lewis structure so we can see more clearly. We cannot add or take away any of the pairs of electrons because we have 12 valence electrons that we have to work with. So we cannot change that number. What we can do, however, is make one of these non-bonding pair of electrons a bonding pair of electrons and form a double bond. Let's see what happens when we do that. So now my new structure looks like this. The first thing I'm going to do is count the number of electrons. I see 2, 4, 6, 8 non-bonding electrons. And then there is 2 more in the first bond for a total of 10, and 2 more in the second bond for a total of 12 electrons. That is how many valence electrons we had to work with. So therefore, that part of our structure is good. Now let's check and see what the octets look like on each of our atoms. The first oxygen here has 2, 4, 6, 8 electrons, 4 in the non-bonding pairs, and then 4 more in each of the 2 bonds. This oxygen also has 4 non-bonding electrons and 4 bonding electrons. They both have 8 electrons, and the correct amount of valence electrons was used. So therefore, that would be a good structure for the oxygen molecule. Rewritten up here for clarity, we have our 2 oxygen atoms sharing a double bond, and each one having 2 pairs of unbonded electrons. For our next example, we will take a look at the nitrogen or N2 molecule, and we will start this example the way we've started all of the other Lewis structures. We will count up how many valence electrons we are going to be able to use to make our structure. So nitrogen, we can see from its position in the 15th column of the periodic table, has 5 valence electrons, and since there are 2 of them, we will have 10 valence electrons with which we are allowed to build our molecule, essentially. And I'm going to start a new count over here so we can keep track of our valence electrons. We move on to the second step, in which we pick a central atom and then connect our atoms to the central atom via single bonds. We do not have a true central atom here because this is just a 2-atom molecule, so we will just simply start by adding a single bond to our 2 atoms. We have used up 2 of our electrons to make that single bond, and so therefore we have 8 electrons remaining to place around the atoms in our molecule. I will put 6 of them on this nitrogen, and that leaves me with only 2 left to put on the other nitrogen. And so we know we've used the correct amount of electrons. We have 10 electrons drawn there. Well, that's a good thing. We want our Lewis structures to only use the allowed amount of electrons, but we also want everything to have an octet within the molecule. We can see that this nitrogen here does have a complete octet with 6 unbonded electrons and 2 bonded electrons. However, this nitrogen here only has a share of or control of 4 electrons, nowhere near the required 8 for stability. So we will try the same trick that we just saw with the oxygen molecule. We will move 2 of these electrons over into another bond with the other nitrogen, forming a double bond, and see how that leaves us. So if we do that, we end up with this nitrogen here. It still has those unbonded pairs of electrons. 1 is moved over here to give us a double bond, and our nitrogen here still has his unbonded pair of electrons. The only thing that has changed is this pair of electrons has now moved from non-bonding to bonding between the nitrogens. We'll go back and check all of the conditions again. Do we only use 10 electrons? I see 2, 4, 6, and then 8 and 10. So yes, we only used 10 electrons total. Does everything have an octet? Well, this nitrogen atom does have an octet. He's got 4 non-bonding electrons and then 4 electrons in the 2 bonds. This nitrogen, however, is still deficient. Even by adding the extra bond, he now only has 6 electrons, 4 in the bonding pairs and 2 that we see there in the non-bonding pair. So this is still not a good Lewis structure because it doesn't satisfy the octet rule for one of our nitrogens. So what we can do is we can actually play the trick again. We're going to move a third pair of our electrons into the bonding position between the 2 nitrogens. What we're left with then is now a triple bond between the nitrogens and one lone pair on each. And I'll just move them to the sides for sake of viewing. But so now again, let's check and see how many electrons did we use. We have 2 in this non-bonding pair, 4 total after counting that non-bonding pair, and then 6, 8, and 10 when we count the pairing electrons. So we have 10 electrons there, which is good. We can only have 10 electrons in this particular molecule. And now we check to see, does each atom in the molecule have a satisfied octet? This nitrogen here has 2 electrons by themselves and 6 electrons in the bonding pairs for a total of 8. This nitrogen right here also has 2 non-bonded electrons and 6 electrons in the bonding pairs for a total of 8. But both of them have satisfied the octet. Only 10 electrons are used, as is expected. Therefore, the correct Lewis structure for the nitrogen molecule shows a non-bonded pair of electrons on each nitrogen, and the nitrogens bonded together by way of a triple bond. In this example, we are going to determine the formula for a compound called methylene chloride, and this compound has the formula CH3Cl. So don't let this be too much of a worry for you. It starts just as we do any other Lewis structure. We count how many valence electrons we are given to work with. So we just need to count up how many valence electrons are found in each atom in this molecule. Notice I say atom because we got to make sure to break down that H3 into 3 individual hydrogen atoms. So carbon, going by its position on the periodic table, should have 4 valence electrons to bring to the molecule. As I just mentioned, each hydrogen will bring its 1 valence electron to the molecule because hydrogen is in that first column. And then chlorine is in the 17th column, meaning he has 7 valence electrons to bring to the molecule. Therefore, we have a total of 14 valence electrons with which we can build our Lewis structure. Now we're going to move on to step 2. In this case, we are going to have to pick a central atom. And the rule states that we pick the least electronegative element that is not hydrogen. If we remember from our periodic properties, if we can just do a little imaginary periodic table here, electronegativity increases as you move from left to right and as you move from bottom to top. So things here have a very high electronegativities, and things here have the lowest electronegativities. If we go by this trend, we would see that the atom with the lowest electronegativity, that is not hydrogen, would be carbon. So the next part of this rule is to put carbon in the center, make it the central atom, and then give everything a single bond to that carbon. So we will single bond our 3 H's to that carbon and our 1 chlorine to that carbon. In doing so, we now have used up 2, 4, 6, 8 of our electrons. So now we only have 6 electrons left to place in our molecule. We start by placing them on terminal atoms first, but we aren't going to place them on hydrogen. You'll notice hydrogens have already actually satisfied their octets in this molecule. Anytime you single bond a hydrogen, you have satisfied its octet. So we're going to try putting those 6 electrons on the chlorine and then checking to see if we need to make any double or triple bonds. We're going to check our conditions for the octets and number of electrons on each atom. The total number of overall electrons used should be 14 since we just used up those 6. We have 2, 4, 6, 8 in the bonds like we've already shown. And then we would have 10, 12, 14 in the 6 that we just placed around the chlorine. So we've used the correct number of electrons. Now the question is, does everything have a satisfied octet? Each of the hydrogens has the pair of electrons in the bond it shares with carbon. Hydrogen only needs 2 electrons to satisfy the octet, so the hydrogens are fine. The carbon likewise has 8 electrons in each of the 4 bonds it shares, or 8 total electrons from each of the 4 bonds it shares, rather. It has satisfied its octet. And finally, the chlorine has 2 electrons in the bond with carbon, and then we've given it 6 lone pair electrons. It has also satisfied its octet. Therefore, what we had drawn before we put all the scribbles on there was a good Lewis structure for methylene chloride. On this slide, we will determine the Lewis structure of phosgene, which has the formula COCl2. We start this Lewis structure like we do all others, in which we count the number of valence electrons we have to build our molecule. I like to list all of the atoms making the molecule out personally and write down how many valence electrons a neutral atom of each has. Carbon has 4 valence electrons. Oxygen has 6 valence electrons, and each chlorine has 7 valence electrons. Adding that all up lets us know we have 24 valence electrons with which to build our molecule. I'm going to list the 24 over here to keep count. The second step of the drawing Lewis structures rules says that we now need to pick a central atom in which to which to attach everything. In this case, we have carbon, oxygen, and chlorine. And the rule says that the central atom should be the least electronegative element other than hydrogen. Since we don't have to worry about hydrogen here, carbon is our least electronegative element and therefore will be our central atom. The second half of that step says to start by writing out your central atom and then connecting each of the constituents to it with a single bond. So we wrote our carbon and then we singly bonded each chlorine and the oxygen to our carbon. That used up 6 of our electrons, so we now have 18 left to distribute. And we can then distribute 6 each around our 3 terminal atoms. Using up those 18. So we've used the required amount of electrons, 18 total, but we can probably see that our carbon has not satisfied the octet rule. To have the carbon satisfy the octet rule, one of the electron pairs needs to become a bonding electron pair. So one of the electrons either here or here or here needs to move into a bonding position here or here or here in order for everybody to have a satisfied octet. So the possible structures for this would then look like this. Now, of course, I could show the other chlorine atom up here doubly bonded as well, but that's pretty much the same thing as my first structure there. So there's really no difference between the two, so I won't show that one. So we really have two choices between the Lewis structures here. And I put this on here kind of specifically. If you could arrive at either of these structures right now, you would essentially be correct. However, in the next section, we will learn that there is a way to tell which of these two structures is correct, and that is by calculating something called the formal charge on each atom and comparing them. Again, we'll get to that a little bit later. Suffice it to say right now that the structure that has the double bond on the oxygen is the correct Lewis structure for the phosgene compound. Here on this slide, we're going to look at the Lewis structure for the sulfate polyatomic ion. This is the first instance where we have a charge on our molecule, so we will see how that affects how many valence electrons we can use. We started the same way by counting those valence electrons, and we will start just by counting how many valence electrons are on neutral atoms in this molecule. So we can see that in a sulfate ion, we have one sulfur atom and we have 4 oxygen atoms. Sulfur typically has 6 valence electrons, as do each of the oxygens. So totaled all up, that means that the atoms bring 30 valence electrons with which to build our molecule. In addition, because we have a -2 charge, that means there are 2 extra electrons in our molecule. So there is a total of 32 valence electrons with which we can build our polyatomic ion. The second step remains the same. We need to choose a central atom, and we're going to choose the least electronegative atom that is not hydrogen, and in this case it is sulfur. So we put sulfur as the central atom, and then we single bond the other atoms to it. So we will single bond some oxygens to it. And by single bonding those 4 oxygens to our sulfur, we have used 8 of our 32 electrons, leaving us with 24 electrons. We can probably see that that leaves us with 6 apiece to distribute around our terminal oxygens. 6 on this one, 6 on this one, 6 on this one, 6 here. That is 24 used, so we've used all of our electrons. If we counted up all of the electrons in that structure there, we would probably find out that we've used 32 electrons. We can then go and check and see, does everybody have a satisfied octet? This oxygen has 8. This oxygen has 8. This oxygen has 8. This oxygen has 8. and our sulfur has 8 as well. Everybody has a satisfied octet. There are 32 electrons used as indicated by the formula and the charge with the formula, but this would be a good Lewis structure. Rewritten for clarity, we have 4 oxygens singly bonded to a sulfur atom, and each of the oxygens has 6 non-bonding electrons. On this slide, we will show the Lewis structure for the nitrate polyatomic ion. We start as we usually do by counting the number of valence electrons we have to work with. Nitrogen atoms come with 5 valence electrons, and each of our oxygen atoms each have 6 valence electrons for a total of 23 valence electrons brought by the atoms. We can also see by the charge on our atom here, we've got a negative charge on our molecule, meaning that one extra electron has been gained from somewhere else. So we can add one more to our total here, 24 valence electrons with which to build our nitrate polyatomic ion. We start by picking a central atom next, and nitrogen is the least electronegative atom that is not hydrogen here. So we will place nitrogen at the center of our molecule and singly bond everything else to our nitrogen. That would be our 3 oxygens. We've used 6 of our 24 electrons, leaving us with 18 more to distribute. And if we distribute 6 each around our 3 terminal oxygens, that will use up our total 18 electrons. Now we would want to go and check to see, do any multiple bonds need to be made to satisfy octets? We can see that each of the oxygens does have a share of 8 electrons, 6 non-bonding and 2 in a bonding pair. However, the nitrogen only has 6 electrons, 2 each in 3 of the single bonds it shares to oxygen, meaning that one of the oxygens will have to take one of its non-bonding pairs and turn it into a bonding pair. When that happens, our new structure may resemble something like this, with one of the oxygens double bonded and the other 2 oxygens singly bonded to the nitrogen. Everybody has a satisfied octet, 8 there, 8 there, 8 there, and 8 there. And the correct number, 24, valence electrons is shown. On the next couple of slides, we're going to talk about some few exceptions that we sometimes run into with drawing Lewis structures. The first one, and probably the most common, are the odd electron molecules. Sometimes when you go and count up all of the electrons for your Lewis structure, you'll see that you end up with an odd number of electrons. In that case, it's impossible for every atom to have 8 because that would add up to an even amount. When that happens, you pick the atom with the lowest electronegativity, and that atom is allowed to miss an electron. It's allowed to only have 7. We have an example of this one on the next slide. So if we are asked to determine the Lewis structure for nitric oxide, we would start this process like we do all of the other Lewis structures by counting up the amount of electrons brought by each atom to the molecule. Nitrogen has 5 electrons and oxygen has 6 electrons. So we can see right off the bat there, we only have 11 electrons that we can use to build our nitric oxide molecule. We don't have to pick a central atom since there's only 2, so we'll start as we always do by connecting the N and the O with a single bond. Then we will note that we have used up 2 of our electrons, meaning we have 9 left to place around each atom. I'm going to place 6 around the oxygen atom, leaving 3 to be placed around the nitrogen atom. So now we can see that we have nitrogen with 2, 4, 5 electrons, and oxygen has satisfied its octet with 8 electrons. So in these cases, it's impossible to move one of these bonds over and get to the octet. We can only move one bond over and get 7 electrons on nitrogen. And this is how the structure would appear. We never go over 8 electrons. We always try to get 7 if 8 is impossible. And we make sure to that the atom that has 7 on it is the least electronegative atom in the molecule. So that's why in this case, nitrogen is the one that ends up with the 7 count of electrons, because oxygen is greater in electronegativity than nitrogen. There are 2 other elements that can be satisfied with lower amounts of valence electrons. So these are kind of in addition to hydrogen. They aren't always this way, but if you end up with either 4 valence electrons on a covalently bonded beryllium atom, or if you end up with 6 valence electrons on a boron atom, these are also stable configurations for those atoms. They are smaller atoms with less electron shells to fill, so they can achieve stability with lesser amounts of electrons. Conversely to the electron deficient atoms, we do have some atoms that can show what we call hypervalency, meaning that they can fit more than 8 electrons in their valence shell. Typically, this happens with central atoms that are rather large. So things like phosphorus and sulfur and iodine and xenon that we see here that are found further down the periodic table where we find our larger atoms. They have d electron orbitals that they can sometimes deal with electrons in and bring electrons into, and so therefore sometimes they can go above the 8 count of valence electrons. These will only usually happen when you have to attach more than 4 atoms to that central molecule. So be on the lookout for hypervalent molecules in those cases. This wraps up the lecture on Lewis structures for ionic and covalent compounds. Here on the last slide, you can find some very good practice for Lewis structures going forward, and you can find the answer to this practice posted on Moodle.